So just to kind of give you a visual, Argonne National Laboratory is about 25 miles outside of the city of Chicago. You can see it down here in the bottom. University of Chicago is a few miles south of the city downtown area. Here's a view from the campus, and a view from Argonne, or view of Argonne National Laboratory. It's about 1,500 acres in a forest preserve outside of the city. About 3,000 people work there. It is a Department of Energy Science laboratory. So when you think about Argonne and University of Chicago, think about Argonne as very much like a university, but without the classrooms. We have students that come and work in the summer. We have postdoctoral fellows. We have most of the departments you would find at a major university. From the standpoint of doing research that is in the urban sciences, I have found that it's quite complementary between a science laboratory and a university, in the sense that what the laboratory has is very strong physical sciences, environment, chemistry, biology, obviously computing sciences, but we don't have economics and finance and social science. On the other hand, the University of Chicago has a long history of studying cities from the point of view of the social sciences and policy. And so putting these things together was our goal with starting this center. And in terms of our choice of working with cities, these are U.S. numbers here, but I think they apply to China as well. And you've probably seen many examples or many presentations on the importance of cities. When we think about cities from a university point of view or from a Department of Energy lab point of view, we think about the fact that what comes together in cities is the greenhouse gas emissions of climate change. It is the use of resources, natural resources of energy, and it's where GDP happens. And so when we think about how to approach cities, we also try to think in terms of across these areas where you might loosely call these, looking at cities in terms of how efficient they are at using, at interacting with the environment, how efficient they are in terms of using resources and moving people and things around, and how well they enable people to go about their lives, to start and run businesses, to raise kids and to have families. And so whether we're thinking about science, or in this case here, I was on this working group last year setting up, developing some recommendations for the U.S. government regarding how the U.S. government could help cities over the next few decades. We also broke cities down in terms of these three areas of environment, resource use, and people. And typically when we look at how to collaborate with other universities and science efforts, we think about the work that we're doing in Chicago with the city of Chicago here on the left-hand side, not just helping them pull data together, but also help them fill in missing data through measurement. We'll talk a lot about that this afternoon. And then there's a set of things that we do to take that data and turn it into an understanding about what's happening in cities. So we have a fairly large and growing effort in machine learning and predictive analytics to help the city of Chicago use that data well, and then take that understanding and try to optimize city services. Not just optimize them from a mechanical efficiency point of view, but optimize them from the point of view of an equitable delivery of those services across the city. And I have a few examples of each of these that we'll go into. Now, when we started thinking about the measurement aspects of cities and developing a platform that we could use to measure cities, we brought these things together, the analysis, the understanding, optimization, and measurement, by developing a platform like you see right here that Pete will talk about, that does not just measurement, but also has the capability to analyze data in real time within that platform. And as we talk about the details, you'll see some of the advantages to being able to pack all those things into one unit out in the city. So with that as a kind of a background, then what we want to do is tell you some things about what we're doing in Chicago, and then after the break come back and have some discussion about how we might find some collaboration here in India. Now, I want to give you some examples here. This is a set of things that we're doing with data, infrastructure, and then measurement. I want to start with just telling you why I started being interested in measuring cities and in taking the data and understanding it. And it was because open data was hitting about 5 years ago around the world in the U.S., and people were doing all sorts of maps of that data, and some of the maps were, quite frankly, sort of appalling. So here's a map, and this is a map of life expectancy in years for the city of Chicago, where you can move like a mile or half a mile in one direction or another, and your life expectancy increases or decreases by 14 years. A map of Delhi would not look different than this. A map of Detroit or San Francisco or New York would look similar, where you have this very different experience within cities depending on where you live. Similarly, with health issues, if you look at Chicago again, now through the lens of asthma, you see the same thing. You see areas of the city where, boy, if I just move my family a half a mile this way or a mile that way, my kids are going to be healthier. And there are some reasonable theories behind this. You can sort of see in the asthma chart, for example, you can see over here as well, that those dark red areas do correspond quite well to high unemployment, to high poverty, to high crime, but there's some component of infrastructure and service that's associated with that we want to try to get underneath and understand by looking at data. Now this is looking at the city as a relatively static entity, but cities are, as you know, very dynamic. And we began looking at measuring cities and then started talking to some of the groups that are optimizing the city on a moment-by-moment basis, like transportation. And we quickly came together with a program called Vision Zero. So Vision Zero is a program that many cities around the world have adopted, and the goal of Vision Zero is to eliminate traffic-related fatalities. In Chicago, the goal is to do that by 2022. That's millions of people just across the U.S. In Chicago, it's about 120 to 150 people per year. And as we start to look at how to help programs like Vision Zero, we need to get beyond just static measurements of cities to understand events and conditions as they unfold. And we'll come back to that when we talk about this platform that we're using for measurement. So one of the first things that we did with the city of Chicago in observing that people were making these maps is we said, unless you're a data scientist, all this open data isn't very helpful to you. So could we design a system that would allow a social scientist or a policymaker, an economist, to look at open data, to be able to search across many open data portals, and to be able to get that data, bring it together, and do analytics? We built this on this here on the right and left, this thing called Planario. It's a geospatial database where what we decided to solve were two problems. One was discovery of data that's spread across many open data portals. And the second was the merger of that data. If I want to do a study of crime in Baltimore versus Chicago or New York, they use different spatial references. The Baltimore crimes are based on some sort of a grid system, and Chicago's latitude and longitude, and other cities might be just a street address. So the merger of data for a data analyst becomes a big part of the investment of asking a question. We want to reduce that investment to asking questions by making data pre-merged. So we built Planario to go out and pull data in from open data portals and then to merge it together so that I, as a researcher, could ask a question like, tell me about this area here, this is in the heart of Chicago, between these two dates. Tell me what data is even available, and I'll then try to figure out if that applies to any of my research. So I've just given an example here, selecting food inspections, and I can start to interrogate that data over here and then download it and do analysis. Well, that's good for policymakers, it's good for, some policymakers, it's good for economists or social scientists, not so much for the residents. So the city of Chicago, although they had an open data portal, worked with us on Planario, and they said, we're going to make something like this for residents. And so they developed this, what you see in the lower left, it's called OpenGrid, and all this runs on commercial Amazon Cloud services, so it's easy to replicate. So we've been using this as a mechanism for infrastructure for putting data out there to make it available to a broad range of people that want to study data. Now, if you really want to understand cities, you have to go a little bit beyond open data and start looking at data that's private. Start looking at healthcare data, and you start looking at employment data or school data, which most every university does. You're dealing with data that's much more sensitive than weather or building stock information or or even 311 or service calls to the city. We're working with NYU and some funding from the U.S. Census Department to prototype a system similar to Plenario, but where you would go in and ask a question about a data set and then be presented with related data from different agencies in the federal government. So that's something that's sort of a preview. That's something that we've just started working with NYU on for the last 3 months or so. Now, I mentioned optimizing cities, and I want to give you an example of using data to optimize cities in a couple of different ways. Here you see food inspections on the right. Because Plenario understands the structure of the data, I can go in and I can refine my search. And I've done it over here. I said, show me not just the food inspections, but show me the ones where risk is high. So the city has done a risk-based approach to food safety inspections based on some data science and predictive analytics, taking into account leading indicators, past inspections, weather events, complaints, etc. And what you see on the left-hand side here is the result of a 60-day trial where what happened was the health inspector, Commissioner for Health, came to the chief data officer and said, I want some help with my inspections because I have 15,000 places to inspect every year, and I have 32 inspectors. That means 500 per year per inspector. Can you help me do a better job of inspecting? So the first thing that we did was to do that rank ordering and then say, well, the typical inspection that you do, this red line here, over the course of, let's say, 1,200 inspections in a 60-day period, catching a certain number of violations, the typical way to do it is randomly go out to the different restaurants and stores. Optimized way to do it is what you see on the left-hand side, and that is let's go to the high-risk places first. Now, the inspectors weren't told why they were getting a list or not, but what we found was on average, that optimized list was catching violations 7.4 days ahead of the status quo. Doesn't sound like a lot of time unless you happen to be one of the people that eats in that restaurant during that week, in which case it's a huge deal. We've got math and applied mathematics people at Argonne that have been working on this and similar problems, and the next step on this one here is to start not just ordering the inspections according to risk, but then mix in some spatial ordering, the traveling salesman problem now applied to inspectors, so that the inspectors can get around and make more inspections more quickly, with the goal being to find violations before they affect public health. An example that I don't have a graphic here, probably the best example I've seen in the city of taking these kind of data and making the city not just operate more efficiently but more equitably is in a rat infestation. So any city that's got water also has a problem with rats, and people can call a number in Chicago and report a rat infestation, and then a crew goes out and does something about that infestation. About a year and a half ago, the city started doing predictive analytics based on about 30 leading indicators and sending the team out to places where they were predicting that rats would be showing up within the next 10 days. The head of the rat inspection, they're called the Rat Patrol, the head of that said that she came across in a part of Chicago that people do not typically call for service, came across the worst rat infestation she had ever found. And that was one that would never have been found if we waited for people to call and ask for help. So this use of predictive analytics done properly can also help get around what is essentially a bias in the complaint and reporting system, where the people who the city is maybe not working for the best are the ones that don't really call and ask for service. People who are more well off tend to call more often. When we started thinking about then measuring cities was when we were looking at predicting crime. These are 866 census tracts across the city of Chicago. We wanted to ask a question with some funding from the Arnold Foundation. We wanted to ask, if we add weather as a predictive indicator for crime, do our predictions get better? We had 8 years worth of detailed crime data for the city of Chicago to work with, so we could do our predictions for 2007 and then look at what actually happened in 2007. We did predictions hourly for a 72-hour span of 3 different specific types of crime. What we found here was, first of all, adding weather as a predictive indicator improved the predictions quite dramatically. Not just the point weather, but the changes in weather. The second thing we found was that in spite of the fact that that did significantly improve things, we only had 6 different weather measurements for this entire 600 square kilometer area. So along with weather, we started looking at air quality and found that for large cities like Chicago or Delhi, you just don't have the measurement infrastructure that you need to make decisions about things like air quality. So, here again, this is part of the city and part of the suburbs, but still about 600 square kilometers. If you're living in this area here, you really have no official word on what air quality is like. And if you compare this to the asthma map, a lot of those red areas on the asthma map are in these places here. Now, Pete is going to talk about the instrument that we're using, but in a nutshell, the reason that you have this sparse set of sensing systems is because they were, by and large, set up a few years ago when sensors were super expensive, and now we're seeing sensors drop in price. With the first thing we saw is sensors dropping in price, but also dropping in quality. We're starting to see the quality come back in these lower cost sensors. So we have an opportunity now, essentially taking advantage of consumer electronics and Moore's law to put a lot more sensors. And the question that we started grappling with 3 or 4 years ago is, could we take an air quality station that would be on a rooftop and cost $1 million and shrink it down into something this big that could be put up on a pole or on the side of a building? As I mentioned before with Vision Zero, we also wanted to be able to look at data and look at activity, and putting computing inside the box meant that we would have some opportunity to make decisions in real time rather than collecting data, send it back to a server somewhere, and then send something to an intersection. Now, we are not, in our project, we're not doing any automated intersections, but we do see the need for the computing right down there in order to support the research community that's doing computer vision and deep learning. So our device then is a combination of measurement and in situ computing to do deep learning right down on the street. When you're looking at a safety program like Vision Zero, we have, and I'll show you a map, we have data that shows where the traffic fatalities are. We have data that shows where all the reported accidents are. What we don't have is near misses. And in any safety program, that's really what you want to look at, is not just the accidents that happen, but the accidents that almost happen. So imagine a device on the corner that's able to learn from the patterns of the intersection and to start to report on things that you wouldn't normally know about, like a near miss, or like, not a problem in Delhi, but in Chicago, like ice on the street that causes the intersection to be more dangerous. So Pete will get into lots of detail on this platform here. I'll just say we've spent, for the last probably 3 or 4 years, we spent about $2 million of internal Argonne research money to develop the underlying platform that's packaged here in this device that you see to your right, to my left. We just got another fairly large internal grant to push further into the deep learning capabilities of the device and to start to look at cooling for hotter climates like you have here in Delhi. And then about a year ago, we got a grant from the National Science Foundation of $3.1 million to take that platform that we developed, package it like this so that it would be not ugly up on the street poles, so that it would be quick and easy to install, and also so it would be quick and easy to replace so that we could upgrade over time at low cost. And then to build 500 of those and deploy them throughout the city of Chicago. We have in-kind partners as part of that project, each of which are doing a different project with it. Intel, for example, is doing the design of our air quality gas sensors, sensor boards. Motorola Solution helped us with FCC emissions testing and strategies. AT&T is our cellular provider. Microsoft is building a portal for high school students and teachers. So we have a number of industrial partners there as well. This is what it looks like. Oh, you can see it here. If you look inside this blue box, you have the computing. Inside this, you have all the sensors. And that's what the first one that went up on the pole a couple weeks ago, that's what they look like. And if you stand back in the intersection, they're actually smaller than they look. That's pretty small when you get it, 5 meters up on a pole. The plan is to take Planario and to provide different ways to view the data for, as with the projects before, for different audiences and different purposes. Here would be, this is a mock-up of one of the first portals that we're doing for the scientist. If you're just a normal person walking through the city, you might want a map that looks like this. And there are 3 different companies that are talking to us and telling us they want the data as soon as possible so they can make mobile applications. Schneider Electric is one of those. And then for some people, they would just like to say, you know, I live right here at about 35th and Western, and I want to know when PM 2.5 is high at the node near me, or maybe I work for the city and I want to know when the power goes out at that intersection. So we're working on, not just, as with Planario, not just the views of the data, but also APIs, the application programming interfaces, so that anyone can build an application that uses that data. And I think I maybe didn't mention before, the array of things in Chicago, all of the data from this goes out as open data as soon as we validate it, so essentially in near real time. Because we have cameras, so there's a camera here that's pointed straight up, and then there's one here that's pointed down at the intersection from about 5 meters above the ground. And because of those, we were very careful how we would approach privacy. In Chicago, somewhat surprisingly, because there are probably 20,000 cameras in Chicago, when we put a camera up that was in partnership with the city and the university and the National Laboratory, it caused some press about the potential for using those images. And so we sat down and looked at privacy from 3 different points of view. First of all, we wanted to design a system that could be controlled to implement a privacy policy, whatever that policy was, that we would have technology that would address privacy. Secondly, we did the privacy in a transparent way, so not only is all the software for this out on the web and available in open source, but we did the development of the policies in a very public way. And then finally, we asked the National Science Foundation to separately fund a privacy oversight group, if you will, an independent group that wouldn't have they wouldn't be able to tell us what we could or couldn't do, but they could advise us through a governance process, so that if we, at some point in the future, decide to add a sensor that has some privacy implication, that's the group that would review our privacy protection strategy. And just in a nutshell, I'm not sure Pete will go into a little bit of this, but this technology for the privacy is part of the reason why having these computers on board is very helpful. So in most cases, in steady state, we'll be collecting multiple images per second and saving a cache of those. Maybe it's 10 minutes, maybe it's 30 minutes. And then running image processing software on the node to extract information from those images. The number of pedestrians moving east-west or north-south, the number of bicycles, number of buses. And then we'll delete those images at the end of that. So by having processing right down in the box, we can also contain privacy in a way that you can't do if you're shipping data back to some central server and then analyzing it later. The initial deployment, which I mentioned started a couple weeks ago, we gave the city this map of locations for different types of experiments, where in this first round out of 500, this is 42, we wanted to get a sense for sensor placement, the number of sensors you would need to answer particular questions. So you can see we have about a dozen. This is an 18-mile stretch along Lake Michigan shoreline, and then a T-shaped here to give us a sense for the lake effect on air quality and weather. Then you see a configuration here in the Chicago Loop, the central business district, where we're along a couple of corridors, and we want to really use that as a test bed to exercise the activity computer vision to look at pedestrian and vehicle flow of various kinds. And then here in the southwest part of the city is it's actually mostly Latino neighborhood where there's some significant air quality issues because of factories, and also this line here is a major 8-lane highway. It's often congested, and so we put sensors down in this area in our plan so that we begin to understand how to do sensing in an urban environment to look at air quality. In doing this, we found that there was actually a fairly straightforward method that we could use to work with the residents of the city of Chicago and the city government to decide where to put these, because some people ask the question, well, how did you decide to go here? And what they mean is, why didn't you put them in my neighborhood? And others are like, well, maybe I don't want them in your neighborhood. Oh, actually, I take that back. I haven't had anyone yet tell them they didn't want them. But what we did was we decided from our experience here that there were plenty of places around the city of Chicago where we could combine a resident concern or an issue of importance to the residents with some group of scientists who, if they had better data, could give some insight into that concern, and then with a policy maker, a person from the city of Chicago or maybe the county that would be interested in acting on that insight if they got it. And that came about because this part of the west side here, we got calls from 2 different hospitals, we got calls from a community group, we got calls from a high school there that all said, we're concerned about air quality on the west side. And then we got calls from scientists at the University of Chicago saying, we're doing asthma studies, can you place some of your nodes around where we're doing our cohorts? And then the city of Chicago also came to us and said, we're kind of wanting to look at green infrastructure on the west side. So we found that where those 3 things come together is the most promising place that we can start to place these devices. I mentioned Vision Zero before, and this is from the Department of Transportation. It's 6 agencies working together, but you can see here they've given us intersections as well as corridors and intersections that are high crash locations. So as we just gave them those 40 locations I just showed you, we're in the process of developing another 50 or 60 to give them next week, starting with these locations here. There was already some overlap. And we're going to be looking at these intersections here, some of additional air quality, and then there are 2 parts of Chicago, that are the west side and south and southwest, that have significant and recurring urban flooding problems, and we want to be going out to those areas so we can start to look at using cameras to detect standing water in intersections. I mentioned Microsoft building a portal for high school students and faculty. The way that came about was I talked to them about this program that we did at Lane Tech High School on the northwest side of Chicago. We took 150 kids through an 8-week curriculum back in the spring that was funded by the Motorola Foundation. We brought in collaborators from the School of the Art Institute of Chicago, the same guys that helped us with the aesthetics of this design. And we said, let's try to expose kids to the process of having a question and then designing a system to answer or get data about that question, then analyzing that data to get some insight into that question. So we took these kids, this is just one of the groups, 150 kids over the 8 weeks, worked in teams of 3 we laid out at the beginning of the 8 weeks all the different sensors that they could use. Each of the 3-person groups came up with an experiment they wanted to do. They designed a sensor system for that, deployed it in their school, and collected data for a couple of weeks, and then did some analysis. So an example, one group put a distance sensor, a proximity sensor, pointed down at the doorway of the cafeteria. They wanted to know what the average height of students were coming through. Another put a pressure sensor on one of the stairways on one of the stairs to get a sense for the use of the stairway. A third group did what they called a social science sensor experiment, where they put a button up on the wall that said, do not push this button, and they counted how many teachers and students pushed that button. We're in the process with that curriculum, by the way, of trying to pull together the teacher curriculum. The Motorola Foundation's asked us to do a follow-on to put the curriculum together in a way that other high schools could use it. The deployment schedule, I mentioned that we've done 2 already. 4 more will go up this week, and then we'll have finished the installation testing that we want to do to then fill out the rest of 2016 with about 10 per week, and then step back, analyze them, make some improvements, add some sensors perhaps, and then do a similar deployment in 2017, only instead of 100 or so, we'll do about 200 in 2017, and do that same sort of evaluation, and then do a 3rd round here. The design, as I mentioned, on the back of this design are just some strap loops. So when these guys go up in their bucket truck, it's really quite fast for them to install these things. The full install took about 2.5 hours, but they've been working ahead of us and doing pre-wiring, and so once that wire is up there, and the bottom of this is, I won't lift it up, and the bottom of this is just a standard screw-in connector. And once that connector's up there, they'll go out with their bucket truck and within a half an hour or so be able to replace these. That was important because we wanted a system that we could upgrade over time. A few other things I never thought I was going to do when I decided to go into computer engineering instead of, say, law or accounting, is work on pilot agreements and legal agreements with cities. But we do have these, the privacy policy and the governance are already out on the web. We're working right now to design a consortium of other cities and universities that want to do this kind of work, where we would also provide them with internal documents that we wouldn't put out except under non-disclosure, like the actual pilot agreement, the 9 or 10-page legal agreement with the city, so that they don't have to take as much time as we did to learn from scratch. So we're hoping to sort of capture all of what I'm talking about in the form that we can pass that knowledge on to other universities and cities. And, even small things like installation. This is the breaker panel here. They are going to give us a breaker. They go down the manhole. They wire it up here. So this process is the process that took 2.5 hours. When we first began to work with the Department of Transportation electricians on this, we had some suggestions for them. They took some of them. They didn't take others. We actually got more help from them on electrical safety and what would make it as simple and quick as possible to replace these things. And one of the things they originally said they probably wouldn't do was to pre-wire, to do all the groundwork before they did this. And then they found out how easy it was to do this first one here. And next thing I knew, they were out and they had pre-wired 20 locations. So we're now behind them on getting them equipment to install. So let me sort of close with what I mentioned before, which is how we want to try to pass what we've learned on to other university or national laboratory / city partnerships. Pete and I were over in London a year and a half ago, and we did a workshop that we organized where we wanted to understand for cities in the UK what their strategy was for instrumenting their city for science. And we had 6 cities come from the UK, plus us from Chicago. We decided to do that again, to bring that same group together, but open it up to other universities and cities almost exactly 1 year ago today. And 15 cities and universities showed up. And since that time, the number has grown to about 60. And so this is part of what's pushing us to try to capture these things, these lessons learned, and also to move this manufacturing process to one of higher volume. The 3 different types of dots you see here, the green ones we've been working with for the most part, other than Denver, which is fairly recent, for quite some time to do pilot projects yet this calendar year, or if not by December, by January. And then red ones are ones where I turned Delhi red, even though it's not quite red yet. We're hoping it is by the end of the day. We turn them from blue to red when we have in place a local partner to work with the city. So it's a university, it's a company, or it's a national laboratory. And when that kind of partnership forms, then we can do what we want to do, which is to give them technology to help them support that partnership. And the blue ones are ones where a university has contacted us or a city has contacted us, and we're working with them to say, well, you need to partner with your local city, or if it's a city with your local university, at which point we would love to support a pilot project. So I'm going to stop there. Pete is going to go into detail about the platform that we're using, and then I think we'll take a break and come back and do some more discussion.
One of the questions that is from a technology standpoint when you look at deploying something is why now? What technology changes or what things are possible that makes it possible to do this now versus could we have done this 10 years ago, right? Or why weren't we doing this 20 years ago? What's different? So one of the big things is that there is a set of disruptive technologies happening, and the array of things, the platform we're using called Waggle, which I'll talk about, is leveraging those disruptive technologies. So there are 3 of them that are happening, and Charlie touched on a couple of them. The first is machine learning and computer vision. And so all of you are familiar with this. I'm going to use both hands for this. There we go. So all of you are familiar with this. You pull out your smartphone and you're ready to take a picture. I pull it up like this to take a picture, and immediately it identifies a bunch of faces in the audience, right, that you're taking a picture of. A little yellow box is now right around Charlie, and if I take the picture, it's focused on Charlie, and the yellow box says, oh, I have a face, so that's what you intended to take a picture of. Now, what didn't happen is my iPhone didn't take a picture and send it to Apple for Apple on their server to pick a face out and then send it back to my camera. That didn't happen. In fact, I can take a picture even when I'm in airplane mode, when there's no connectivity at all. All of that processing, all of that computer work is happening. Okay. Well, I don't have four hands. If I did, I would use both. But all that's happening in the device. And so what's happening here, what's unique, the disruptive technology that the Array of Things and other kinds of sensors are using is this revolution in machine learning. It's what's making autonomous vehicles possible. It's what's making pedestrian counters possible. What's making being able to count mosquitoes with cameras that look at sources, right, carbon dioxide sources and others. All of that kind of thing, which is computer vision and machine learning. That's one disruptive technology that's being put to use. It's the question, why now? The second is a technology question with respect to the sensor. As Charlie pointed out, in the past, sensors were very big and very expensive. Now, sensors are using the same process that we use to make silicon chips. So when you make a chip, a silicon chip, you're essentially printing on silicon. That same process, whether it's graphene, carbon nanotubes, something else, that same process can be used to make sensors that measure everything from nitrogen dioxide to methane. And so this is actually a picture of some of the disruptive sensors that are being made by a company in the US. They're being made in India. They're being made all over the world, these kinds of sensors. And Intel is packaging them up and working with us as a partner. This is a carbon nanotube and developed at Argonne National Laboratory. And this carbon nanotube senses methane. And so it's a very cheap, again, carbon nanotubes are extraordinarily cheap. Being able to make a sensor that's extremely cheap that could sense methane that you could deploy ubiquitously is a big game changer. So it's these two technologies combined with low power CPUs that we get from our smartphones that's really making it possible to, in a smart way, use technology to instrument things and move forward. So that's the backdrop. Now let's dive in real quick as we talk about this. So the platform that Charlie pointed out, the platform that's been developed at Argonne is a yeah. On this platform, we support all three. So we support Bluetooth connections, Wi-Fi connections, actually an old-fashioned cable connection for some of the rooftop deployments, as well as a cell tower. And our partnership in the city of Chicago is with AT&T, who has provided that for us. And so this platform was developed at Argonne, and the platform allows us to control these components in a way that is very reliable. We need it to be, I say here, hackable. That's in the good sense of the term, not the bad sense of the term. The good sense meaning I can add new sensors and I can change what I'm sensing. If there's a new disruptive technology, I can integrate it very quickly. So following up on that computing platform piece, so my day job is usually supercomputing. And I used to be the director of the Supercomputer Center when we deployed a supercomputer at Argonne called BlueGene P. And then I designed with IBM the supercomputer called BlueGene Q. And one of the interesting things is that the power of these very advanced supercomputer platforms is the same sort of technology, and it's becoming very powerful, of what you carry in your smartphone. So this is the smartphone CPU packaged up something bigger than what's in your smartphone. And the comparison in processing power is only 1 or 2, 3, factor 4 difference between the kind of node, the compute element we use in a supercomputer, and what we're carrying now in our pockets. So the ability to do computing at the edge, for me to look at video, at audio, to detect things, to process that data at the edge, that is the explosion. That's the new piece that we have. As I mentioned, these sensors, carbon monoxide, sulfur dioxide, hydrogen sulfide, this is just one set of sensors. Other companies are developing sensors, and one of the reasons we're here in India is that there are a number of universities in India developing MEMS, the microelectric, mechanical devices, nanotechnology sensors, and we wanted to put those into deployment as quickly as we can. So this comes from University of Illinois in Chicago, and this is printed silicon. So this is a channel, it looks like a 3D map. Here it is, right? So air comes in here. It is sort of split at these sharp edges, and it sends the particles into two different bins, and those bins then land on what's essentially like a microphone. It's a very small MEMS resonator. Those particles are sticky. They stick to the resonator, and they change how the resonator vibrates, and then we can measure how much particulate matter someone's breathing. So this device is about the size of your thumb, and it's meant to be worn. The current work they're working on is a wearable sensor, in this case, and Intel has been partnering with them on wearables. But it's the kind of lightweight sensor that we can deploy ubiquitously with platforms like what we're talking about. And it's this disruptive technology where printable silicon is extremely inexpensive. This is the sensor array now, which is inside this plastic housing here. In the U.S., we refer to this as a Stevenson shield. It allows the rain to go over the top and fresh air to come in that we're sampling. And so what we see here is inside that pod, here's the camera that's pointed down. There's also a camera that's pointed up in the other location. This are the sensors that measure nitrogen dioxide, hydrogen sulfide, and so forth. This is a particle sensor, and this particle sensor has been hacked with cooperation with the company. We have a little special sticker on here because this is now not measuring the PM 2.5, but measuring pollen ranges. So pollen particles are much, much larger, and so if we want to study asthma, we can change the software in this same device. It's the exact same device. We change the software in this device, and then we're able to measure pollen instead of PM 2.5. This is a real picture, but I've sort of stylized it here because from the privacy policy perspective, we're not sharing pictures yet of what we see on the streets. So this gives you an idea of what a camera, this is deployed in the city of Chicago, what we can see. In this case, we have a garbage truck going by and a couple vehicles here. There was a pedestrian here. It's kind of hard to see with the blurring. And this is what is the input to the machine learning code that I talked about. And this is stuff that many universities here in India are already working on, computer vision, game controllers, all of that technology that's machine learning and computer vision can be applied to city data, to data that we collect from audio sources and from camera sources. One of my students from Caltech, I made a cultural reference to the Beatles and the Abbey Road, and he had no idea what we were talking about. So then he had to go look it up on Wikipedia, and after looking it up on Wikipedia, he then applied the computer vision algorithms to find people and cars in this classic picture. And here he's found several people. In this case, it looks like, well, maybe this is the algorithm thinks there's two people here. It's kind of fun here that it found a 1960s Beetle. And so these are the kind of algorithms that people are using. These are very, they can start out very simple. These are things that grad students are downloading and using, and then they become very sophisticated as they expand them. Like, for example, one of the things that Charlie mentioned is we're interested in what happens in traffic with near misses. That's a hard thing. This is a counting problem, right? Is there a human? Okay, this is what a human looks like. Is there a car? This is what a car looks like. For a near miss, I need to calculate a trajectory of a vehicle. I need to see that a pedestrian maybe has run backwards or the vehicle has swerved. That's a set of dynamics that I need to have a grad student, a postdoc work on. And once they've completed that, though, you can imagine loading that up into the array of things box and just getting a sense of which intersections are more dangerous, what times of day. Even if there's been no fatality, you immediately could get a pulse of what's happening. And also when it's raining, what's changed? Do we need to change the lights, the traffic lights? We're talking to General Electric, who makes makes lighting, right, for the city, night lights, LED lighting. And one of the things that they said was, well, when it snows, the reflectance of the snow changes how much light we need to apply in order to light up an intersection. So we want to automatically adjust the power and adjust the lighting situation based on what's happening on the ground. All of these things relate to this sort of smart computer, machine learning, and vision. Samples of this, one of the biggest ones that we're very interested in is water. So West Chicago has a very bad flooding problem. This is a picture not from West Chicago, but it shows this contour line that you and I, as humans, can easily pick out. A computer algorithm can do this too, and we see standing water. This tells us that the drain system is not keeping up with the water that's accumulating on the street, and this is a problem, right? Eventually it backs up into people's homes, and we have sewage that backs up into people's homes in the west side. So this is a computer vision problem. This is a computer vision problem. This is a one where a human used to go out and read this to see what the water level is. This is a very easy to change to a computer vision problem. We have folks who work at a local forest preserve who want to monitor frogs. This is an audio problem. The frogs, this isn't the picture of the frog of interest, but the frog that they're interested in only vocalizes twice a year. So for 2 nights, it's like speed dating for frogs. That's when everything happens. And so for them to go out and study the frog, they really need a sensor to tell them when the frogs are chirping, because they can't go out every night in the summer and try and see what's happening. We've done a lot of testing on these nodes. As Charlie pointed out, some of the nodes are in an environmental box that just goes out into a field. So we refer to this as the ugly box. It's not as sophisticated as this, which included the School of the Art Institute doing the design and so forth. So these ugly boxes are currently at a field, for example, being tested. This is an infrared camera image of the nodes themselves, making sure the circuits are working. And we've also had this tested with FCC approval, so that this is a radio box, essentially. This is a big, huge antenna, and they're looking through to see if there's any interference. So I can deploy this safely in a city and guarantee that I'm not disrupting cell phone communication or Bluetooth communication or anything else, because we've done the right thing with shielding. This is the computing parts in this box here. So if you could open that up, you would see our boards in here and our CPU and the other components. Here we've laid them all out on the table. Charlie pointed out this morning, I don't have a picture of the microphone, but we have the camera, the light sensor, infrared, ultraviolet, the chemical sensors here, nitrogen dioxide, hydrogen sulfide, pressure, sensitivity, vibration, a magnetometer, and so forth. We've done deployments in other places aside from the city. One is at a prairie site nearby. This is near Chicago. It's a big open prairie with water, and we're setting up sensors there. We've given the sensor pods, the internal guts of that, to a company in New York City that has deployed several hundred of these advertising kiosks and telephone kiosks, and they have 40 of our units that are being slid into this kiosk so they can turn the kiosk, which is street infrastructure, into sensing infrastructure. So can they make it something that senses carbon dioxide, carbon monoxide, so forth. Also the same thing for this trash can company that makes solar-powered trash cans. And this is a deployment here in Chattanooga, which is measuring pollen, and there's an NSF funded project to understand pollen and kids and ragweed season. So this is supporting that. So the team is quite large, and we have a set of usually 5 to 7 students every summer from various technical universities. We would love to have more come and visit as we work each year on improving the platform. So to wrap up now, we have a couple disruptive technologies that are driving the capability for smart cities and smart urban infrastructure that Charlie pointed out. Machine learning and computer vision, nanotechnology, MEMS devices, graphene, so forth, this low power CPU and networking, as you pointed out, and the fact that it's completely open source. It's totally open for any student, for any postdoc, for anyone who wants to modify it, add their own piece. And in fact, we're having a workshop in a week on the 20th at Argonne, and one of the people already said, I want to bring a GPS, because they want to hook their GPS in. For our purposes, we know where we're putting them. You know, Charlie has mapped out every street corner. They know exactly where they're putting them. For other applications, they need to keep sort of track of where they are, and so they want to add a GPS as an example. So to wrap up, from the perspective of the technology, there are many collaborative possibilities with what's happening in India. We're very excited about computer vision and about machine learning and also big data, doing analysis of the data, and also novel sensors, electrochemical sensors, gas sensors, MEMS devices, nanotechnology. And these things we want to integrate and try as quickly as possible on the platform and to see what's possible with the city of Chicago.
I'm going to talk to you a little bit about a new center we've developed here called the Tata Center for Development at UChicago. By way of introduction, I'm Anoop Malani. I'm a professor at the law school and the medical school. I'm a faculty director of both the Tata Center for Development and something called the International Innovation Corps, which I'll tell you about in a second. But my background is as a social scientist. So when I look at the sorts of work that Charlie and Pete do, I think of myself as a consumer of the data that they produce, and I think about what I could do with those data. And what the Tata Center is an institution that helps other consumers use those data. So let me explain a little bit more. So I'm going to first give you a little bit of history and motivation for the Tata Center, talk about the structure of the Tata Center, and then talk about future directions of the Tata Center and how it ties in to the array of things. Okay, one thing you'll notice is I don't have pictures. So economists are notoriously bad at communications. So we just toss text up in order to compete. So let me tell you a little bit about the Tata Center. So the Tata Center just started this year in April, but it actually emerged out of years of prior work that we've been doing, mainly research, and then also something new called the International Innovation Corps that started 3 years ago. And the logic for this is for the Tata Center was really that when you and the University of Chicago has been doing research in India for many years, not just humanities research, but also social sciences research, and increasingly recently has been impact evaluations of development interventions or government projects. And that sort of research, we're very excited by that because it's increasingly accepted as important. You had organizations like 3IE and JPAL and development agencies that recognize the importance of these evaluations. The difficulty is that they're not always acted upon. Okay? Sometimes when you do the research, the fact that you show a particular intervention work doesn't necessarily mean that there's going to be a policy change that we see in the world as a result of that. Even when you see sometimes policy changes, if you look carefully, you'll see that policy has changed de jure, but de facto nothing's changed on the ground. The policies are not implemented or not implemented effectively. And we think the reason why is really twofold. One is that the entities that are in charge with implementation, largely government officials, but sometimes also NGO officials, they're not reading academic papers and think tank reports. That's just not what they do on a day-to-day basis. They're not because they don't want to, but because they're too busy with their day-to-day activities that they don't have time to sit around and read journals. Also, even when they do know that, the Indian government, while an amazing apparatus, is in very important ways constrained, capacity constrained. And what we think is it's capacity constrained because it doesn't have a lot of high-quality individuals. I mean, that go into the government. It's not it's not as high-class a job or as prestigious as a job as it once was. And there's a lot more competition from the private sector for jobs. And so high human capital graduates tend to go to the private sector rather than the government sector. So these two things, I think, make it so that research alone is not enough. So what we did is we said, okay, let's work on creating something that would build capacity within the government. And so we started something called the International Innovation Corps in 2013. So that's not 2013 years ago, it's 2013, 3 years ago. And the reason is because when we were doing research on the ground in India, often, again, involving the government, we found that the government would come back to us and say, instead of just evaluating our program, why don't you help us run it? Right? So, for example, I'll talk about a health insurance program we're working down in Karnataka. We were doing an evaluation of the impact of that public health insurance program on health and on the finances of beneficiaries. But the government and the government said, look, in order for you to do this work, we have to implement this properly. And instead of just trying to evaluate, why don't you help us implement it properly so that it works better? Why don't you help us figure out how to improve uptake into the government scheme so more people are enrolled? How do you make sure that people understand how insurance works so they're utilizing insurance? How do we stop fraud at government hospitals? Things like that. So that's the sort of questions they asked. And it wasn't just with the projects that we worked on. As other people found out about, other government officials found out about what we were doing, they would ask for help there, whether it's working on the PDS scheme or Aadhaar and the like. So given this need, we decided, this is something that's a little bit different than what we do in terms of research. But it's related. It uses the same sort of analytics. So we decided to create, it's very hard to describe this, but I would think of it as something like a social impact logistics firm. What it does is it's an organization that goes and helps governments, sometimes NGOs, implement scalable, large impact development projects or solutions. And I'll give you some examples of that in a second. But the methodology is once we identify a project, we send a team, a multinational team of 4 to 5 individuals to work with the government or with the NGO in situ, there for at least a year, implementing whatever their project is. And again, I'll give an example in a second. And the individuals that comprise these teams are recruited by the University of Chicago, typically from graduates from the University of Chicago and from local Indian universities. And they're graduates chosen because they have some skill, some training that's appropriate for that project. And what we do is we supplement that with a training program that's mainly done at the University of Chicago. We teach them things like project and team management. They already have some substantive training or prior experience. So we need to just get them to be able to work more effectively as a team in the field in implementation. So let me give you some examples. This is just a subset of projects that we worked down. So for example, there's this organization called the Delhi Mumbai Industrial Corporation, Industrial Corridor Development Corporation, whose job it is to build cities, greenfield cities, along a tract that runs from Delhi to Mumbai, 24 cities. And what they needed to do is design those cities. Among the things they need to design is the regulatory structure for the cities. And so we helped them out by setting up a single window option and getting that through legislatures in the 4 states in which DMIC was working. And so that's a template, a regulatory structure that can apply to all 24 cities. And we did some other work for them, but that was our main accomplishment. We also worked with a government corporation called Central Electronics Limited, and what they want to do is work on rural electrification. And so we identified for them some microgrid solar technology, solar panels and metering technology, and an NGO that knew how to deploy these and worked with the NGO to actually pilot these in 34 villages and assess their impacts and adoption. And now it's being scaled by CEL. We also helped an organization, a public-private partnership called the National Skill Development Corporation. Their job, NSDCs, is develop strategies for job skilling in 23 different sectors in India. There was one important sector that they hadn't developed plans for, which is the textile sector. It's the 3rd largest sector by employment in India, about 40 to 60 million people involved in that sector. But it's a challenging sector to work in terms of creating economically viable job training programs. And so we work with them in trying to devise these sorts of programs and came up with some interesting ideas for how they could do that. We also worked with a combination. So Haryana, the consulting for BCG, and the Michael Susan Dell Foundation to help set up an MIS for the school education department in Haryana. And one of the key accomplishments when we did that right away, we were able to reduce, for example, the number of schools that were understaffed with teachers, just by identifying places where teachers are misdeployed and deploying them to understaffed districts or understaffed schools. We also worked in areas that you might consider a little non-traditional. So there was an organization called Millennium Alliance. It's actually a social impact investment fund created by a number of entities, including USAID, DFID, the Ministry of Science and Technology was involved, ICICI Foundation, FICCI. And the challenge was how were they going to run this social impact fund? It was about a $50 million fund. And so we brought in the IIC to help them develop new application processes to when potential applicants apply to get funding, to kind of set up a screening process for them. We also, importantly, once portfolio companies were selected, you need to have incubation services to help those organizations, learn how to do accounting, how to think about logistics of scaling their product and the like. So we worked with them on that. So these are just some examples that were implemented. But and they all sound good. We wouldn't have done them if we didn't think they sounded good. The problem was, if you ask me, were they effective? My answer is I don't know. Right? I don't know if they're socially beneficial. I just know that they were implemented well, or at least according to the metrics that we came up with. So the IIC was a good first step, I think, but it was just a good first step. We need more. We need to figure out if it's actually having effect. So here's what we know. We know that research, or at least based on our experience, research alone is not adequate. We need some implementation. But when we try to implementation, you can't just do implementation alone. You need some evaluation. You need some research to know that it works. So you need to do both those things. But at the same time, doing those two things and just issuing a report is not enough. You need to disseminate that report to the people that can act on them and get them to act on it. And so our theory is that what you want to do is train government officials. You want to set up an executive education program for government officials, disseminate your information that way, so the government officials know directly, like they are paying attention and they know how to translate that into action. And you can turn back around and help them implement stuff. So here's what we did. So with help of the Tata Trust, the University of Chicago Trust here in India, and the University of Chicago back in Chicago, we established the Tata Center. And the whole idea is that we tackle problems by combining research and implementation and then disseminating the results through government training. So that gives you a brief structure of what the TCD looks like. We work in, as I said, we do three things. We first identify a problem and a solution that we want to work on. We implement a pilot, often using IIC teams. We evaluate the impact of that pilot, working with University of Chicago and partner faculty, which I'll explain in a second. And then we create training modules and to disseminate the results. And these are training modules for government officials. We work in three verticals, health, as of now, health, water, sanitation, and energy and the environment. And we partner with other organizations at the University of Chicago. In fact, you should think of the IIC as a separate organization that the Tata Center partners with, also with EPIC, which works on energy policy and environmental policy at the university. Okay, so let me give you two examples. One I already introduced you to. So this is healthcare access in Karnataka. The problem that we wanted to tackle was how do you best provide healthcare access to middle-income populations? You might ask, why middle income? Why not lower income? Well, as it turns out, the government already has public health insurance schemes targeted at lower income populations. And commercial insurers largely target the higher income populations. But there's this big, let's say 600, 800 million large group of people that don't have access to healthcare financing or effective access to healthcare financing. So one possibility is to say, okay, the government should expand its public health insurance option, the one that's targeted at below poverty line populations, expand it to above poverty line populations. And so that's what we did. We piloted and evaluated an extension of the public hospital insurance scheme that the government has, Rasya Swasthya Bima Yojana, RSBY. We did is we piloted an extension of that program to above poverty line populations in Karnataka. And we did this pilot with the help of the IIC, but also with researchers from University of Chicago, led by myself, Northwestern University, Princeton, University College London, and ISEC in Bangalore. And as I said, our implementation was not just for the pilot, which is important for the research, but also more generally, because the work that we're doing to do the pilot is also something that can be used to make RSBY generally more effective. So the IIC team is helping the government of Karnataka implement enrollment, information campaigns, hospital empanelment, doing data analysis, for example, to detect fraud in claims, things like that. At the end of the day, we'll produce a training case study, just like an HBS case study, but for a government project, and we'll deploy that via an executive education program, specifically a health policy class that'll be part of that. executive education program. Let me give you another example. So this is in the water vertical. So the question here is, how do you address irrigation challenges, particularly given the variability and unreliability of monsoons? So now the solution that we want to work on is not a solution we came up with. It's the government of Telangana, one of their kind of marquee projects to tackle this is something called Mission Kakatiya. And they're trying to rehabilitate 46,000 water tanks throughout the state, basically to promote rain capture and then use gravity-based irrigation in lieu of pumps, in lieu of wells. A little bit more energy-intensive a solution. So what are we doing? On the research side, what we'll do is we'll look at the impact of Mission Kakatiya on crop yields and aquifer health. We'll work with researchers from UChicago, Berkeley, and the World Bank. Along the way, we're going to be working with faculty from the Institute for Molecular Engineering, a guy named Suptik Guha at University of Chicago, to basically try to use satellite imagery to measure yields more cost effectively and objectively. In terms of the implementation, not only are we going to help with the data consolidation and setting up an MIS in order for us to be able to do this evaluation, but also to work on what are called agricultural extension activities. So it's not enough to just rehabilitate a water tank. What you want to do is you want to couple that with training on how to use the water tank, how to combine water-based irrigation or gravity-based irrigation with bore wells, also proper crop selection. Make sure you don't just immediately opt for more water-intensive crops. Also things like how do you get things to market and pricing and the like. So we'll be doing that. The IIC will. And again, the training is a case study that'll be produced, that'll be disseminated through a water policy class. I want to talk a little bit, because Ranjan Daniels is in the room, and he's helping us develop, he's a dean over at the Harris School. He's going to help us develop the training program within the TCD. And the key thing for us is that we're going to be working with partners like ASCI, the Administrative Staff College of India, and the Tata Institute for Social Sciences. We'll work with partners to set up a what we'll call a modular executive education program. And this is currently our plans. We hope to have the first pilot running by 2017. But basically, we'll offer some substantive courses, some methodological courses, unsurprisingly coming from the University of Chicago. So as I mentioned, there'll be a health policy class, a water policy class. We'll also work on an energy or environmental policy class as well. But then we'll also offer classes in methodology. So data analysis, mainly it's not about learning how to code, but really learning how to consume data. So government officials need to understand how to interpret data, what sort of data to ask for, and things like that when they're running a program. Basic microeconomics to do cost-benefit analysis and the like, and also borrowing some classes or methodologies from the Booth School of Business. We'll also teach a management class. And the goal here is to have modules that use case studies, like HBS case studies, but for government programs. Each of these classes will last we expect to last about 2 weeks, so that's about 8 half days. Now I need to tie this back into what Charlie and Pete were talking about. So we have here, what we want to think about is future directions for TCD. We've got a basic structure, we've got a series of projects going, but we know that I think to even become more effective, we have to go a little further upstream. So there are 2 ways that you can do this. One is that you have to find solutions that you want to pilot as part of the TCD and solutions that you want to evaluate as part of the TCD. When these exist, we're fine, but when they don't exist, we need to invest in what I call ideation, come up with new solutions. And so we've got 2 strategies for this right now. For example, we're sponsoring an urban challenge run by EPIC and by Urban Labs, another organization at the University of Chicago. It's an urban challenge being run in Delhi to understand or tackle air pollution. Entities are asked to propose solutions to air pollution strategies. These entities are typically NGOs or government officials. The winner gets funded in order to basically act on or develop their solution. We're also beginning the IIC is a partnership with OpenIDEO. OpenIDEO is a division of the design consulting firm IDEO. They developed a crowdsourcing internet-based solution platform to identify new solutions to problems, including development problems. And so, for example, we're going to work with them to run this sort of crowdsourced solution platform or concept on sanitation policy. One of the things that hopefully we'll discuss with them later this week is thinking about doing it, for example, with improving the maintenance of toilets in slums. Something like that. And then once they come up with a solution, then we'll plug it in the TCD model and the IIC will implement it and it'll be evaluated. But we're also interested not just in ideation, but also developing the data required to do the sorts of evaluations that we want. And this is why we see our Urban CCD in their work, and particularly the Array of Things device, is so promising. So the idea of being able to bring that device, for example, to Delhi and deploy it throughout the city allows us to generate the sorts of data that you would need, now thinking about examples of consumption, the data we need to evaluate policies. Who's the person from Epic? Step out. So last year, Epic had worked, actually it's earlier this year, worked with the city of Delhi to evaluate their odd-even intervention, right? And if you have array of things, you could almost do that on a real-time basis. So you could use the visual sensors to measure traffic to see if traffic went down. You could use the air pollution sensors to see exactly where you saw air quality benefits, how those were distributed, and the like. And you'd be able to do that immediately, using the data to calibrate exactly what you ought to be doing. Right? That's really nice. Okay. Let me flesh out a vision for what we think of, a vision we have for TCD and why the people that are in this room specifically were invited. And hopefully there'll be even more people coming in. So our first goal is to partner with an Indian city. I think Delhi is a great first step. We have been in nice discussions with the Delhi government to basically get the permission we need to deploy a handful of sensors around the city. And the pilot actually that we'd like to run this year, maybe of 5 or 10 or 15 sensors, is partly to develop the sensors. So the sensors are developed for Chicago, where there's different set of environmental conditions, different set of sensors that you'd need. So for example, you have to be more robust to the cold. Here you need to be robust to heat and to really tough monsoons, depending on where you deploy it. Also different level of dust that you'd have to address as well. Also, the other thing that we want to do is work with local groups to identify what sensors we actually want to put on this array, what sort of data analysis we want to do with the visual data that comes out of this array. Doing traffic analysis in Chicago is different than traffic analysis in India. As Pete pointed out, it's really important to post that data on a platform such as Planario, make it publicly available. I mean, we like to think that what we're doing is creating a public good, partly not just because we have this commitment to open data, but because open data allows other people to figure out new solutions that might arise from the data we produce. We don't have all the imagination in the world to know every possible use of the data that we have. So there's a lot of social good that can come through public use. It's very important to us that we work with local universities. That's why we have invitees here from IIT Bombay, IIT Delhi, but that's not just those schools, but other technical institutes to really work with us to kind of employ the data that could be created, gathered by the Array of Things and presented through Planario to answer policy-relevant queries. So traffic is a great example, I think. I know that there's a lot of interest in that. And the goal also is to invite foundations and corporate partners who can see the social benefits that come from this sort of platform, this sort of collaboration, to join us. Obviously, let's be brutally honest. Somebody has to fund this. Somebody has to serve as the platform, as kind of a local partner to really house or protect this. And those local partners are local corporations and foundations. So anyway, so let me go ahead and stop right there. I've gone on long enough, but hopefully you see the kind of the overarching goal that the University of Chicago has in Delhi, and then how in India, not just Delhi specifically, and how the partnership with Argonne and specifically the Array of Things project fits in.